Good evening, everybody, and thank you to Graham and to Science Foundation Ireland for their support of this series, and also for supporting the importance of engaging the public with science and technology. And that's something that the Science Gallery is very committed to, and it's something that we've had the wonderful opportunity to work with the World Science Festival in New York for 2 successive years now, and it's really, for anybody who hasn't been to it, it's an absolutely fantastic event. This evening we're going to be exploring the boundaries of science, the boundaries of inquiry, and we're going to be exploring with Brian Greene the role of wonder and mystery in science. And those are 2 words that perhaps we don't always associate with science. Some people think of science as all about certainty and all about getting the facts right. But we're going to try and open up that question, and it's going to be a conversation, a free-flowing conversation. There's going to be plenty of opportunity for you and the audience to get involved and join the discussion. So please do think of questions, whether they're about string theory or multiverses or some of the other things that we might explore. But before we get into that, I wanted to start with this quote from Einstein, which is a quote that I think Brian Greene finds inspiring and interesting, and it's something that I find fascinating, as almost a confession from a scientist about wonder and the mysterious. And Einstein said, "The most beautiful thing we can experience is the mysterious. It is the source of all true art and all science. He to whom this emotion is a stranger, who can no longer pause to wonder and stand rapt in awe, is as good as dead. His eyes are closed." And I would like to ask you, Brian, what does that mean to you as a scientist?
Well, it's interesting. I only actually know the first part of that quote, the first sentence. I'd never heard the second part, which I think really brings out, it's amazing how people, in this age of trying to have quick quotes, they actually wind up cutting out the part that really matters. And I agree with it fully. I mean, the most amazing thing about the scientific journey is that we spend most of our life in the dark. We spend most of our life trying to figure things out. And most people don't recognize, but maybe people here do, 99.9% of everything we do is flat out wrong. And it's not wrong because we make mistakes. It's wrong because the universe is such a rich source of mystery that our attempts to understand it are usually off the mark. So, if in your lifetime you have 1 or 2 or a couple great discoveries, that's spectacular, but the wastebasket is full of things that just went nowhere. So it's all about being comfortable searching in the dark. I mean, the other Einstein quote that I know along those lines is when he spoke about the general theory of relativity years later, right? He published it in 1915, late fall 1915. He, decades later, described the search for general relativity as years of anxious wandering in the dark for a truth that he could sense but couldn't quite see until finally he emerged into the light. And that, to me, is what it's all about. The problem is most of us don't ever emerge into the light, but that's what the journey is all about.
And is wonder something that even on a day-to-day level in your work as a scientist is important to you? I mean, do you sort of have, in your calendar, your schedule, do you have like 10 a.m. wonder for 2 hours, or contemplate the mysterious, or...
I wish it was as romantic as that. That it's not. And the problem is many students come into science having read various books, and at least I do try to bring out that sense of wonder and mystery. But when they have to learn the mathematics and actually get down to brass tacks and really dig fingers into the details, often that's a turning point for some students. They're like, whoa, I didn't realize, behind all of this was very rigorous thought. And so the bulk of what we do is not sitting there in wonder and reverie. It's, doing the calculations. It's writing the computer programs. It's doing the simulations. It's trying to figure stuff out. And I do try to pull back on a regular basis and recognize what it is that we're trying to figure out. I mean, those calculations, those are really trying to figure out some insight about the origin of the universe. Those calculations, trying to figure out something about the nature of unified theories. But when you're deep in the details, it's often hard to get that sense of wonder, and you do have to, in some sense, train yourself to pull back and see the bigger picture now and then.
And I'd be very interested to know a little bit more about what it was that really sucked you into science. You know, was there a moment, an inspiration, some sort of experience that triggered that interest? What was it?
I don't know if there was really a specific moment, but there were moments that certainly stand out for me. I remember one, I grew up across the street from a planetarium in Manhattan, the Hayden Planetarium. And basically, whenever it was raining outside, that's where my mother would send me to get me out of her hair, kind of. So I'd wander around this planetarium. And, you know, I think by the time I was in 6th or 7th grade, I got a sense at that place of how fantastically minuscule and unimportant we all are. I mean, when you're comparing Earth to the solar system, to the galaxy, to the 100 billion or so galaxies that we know are out there, it does give you a sense of kind of being puny. And it just began to well up inside of me that, people have been asking why we're here for a long time, but there clearly wasn't an agreed-upon answer that had been sort of set in stone. So it struck me that maybe the best way to get a sense of meaning against this backdrop of enormity would be to just figure out not why we're here, but how we're here. How did the universe come to be? How did the stars come to be? And as I began to realize, that was the domain of physics.
And was that still as a child? I mean, that you were engaging?
You know, sort of 12, 13 or so. And that really propelled me forward to say, try to put the why questions to the side and just try to do the easier how questions. And that's really what drove me forward.
Interesting. I'm delighted to hear as an Irishman that it was the rain that drove you to science. But you know, how did that journey progress? I mean, did you... so you then went to university, I suppose, and how did that progress as an area of curiosity? And I like the how questions rather than the why questions.
It started more in mathematics, so sort of learning the language of the universe in some sense in mathematics. And when I began to get the facility of how you apply mathematics to solve real problems, that to me was also a vital one of those inspirational moments. And that one I remember specifically. It was high school physics, and the teacher set us this problem. You had a piece of chewing gum attached to the ceiling and attached to a ball, and you swing the ball. So as the ball swings, the chewing gum stretches. Figure out the trajectory of the ball. And, you know, it's not a hard problem when you learn the basic math behind this sort of stuff. But I remember solving this in my room and running down the hall to my father to show him the result, you know, not because I thought he was an aficionado of chewing gum and balls kind of thing, but just this idea that you could do math and figure something real about the world out there was just sort of an amazing idea to me. And that propelled me to study a lot of mathematics, but always with the idea that physics would be the place where this mathematics would be applied. So I did that in college, and, you know, graduate school, I was at Oxford, you know, here, and when string theory, this approach to unification, really bubbled up, which was 1984, that was my first year in graduate school at Oxford, and it was really a godsend, because here it was the need for heavy mathematics applied to some of the biggest physics questions of the age, the ones that Einstein sought but never found, this unified theory, and that's where all my effort went.
Yeah, so what was part of the joy in that, the kind of the joy of solution that mathematics can provide, like the kind of, you know, getting something out, and so was that, you know, the sort of the pleasure of the elegant solution, was that an important thing for you? Or?
It was definitely a big part of it. The other part of it is it's a great thing that you have these big questions that might be susceptible to a language that has very certain answers. So back to your earlier question about sort of the wonder and the uncertainty, sure, we wander in the dark, try to figure stuff out, but the great thing is, if you are on the right track and doing things in a way that's really relevant to reality, then whether you approach it this way or that way, whichever mathematical techniques, whatever approach you use, it's all going to converge on the same answer. And that's wonderful. I mean, we see that today, right? We have this archive where all the new papers that people write are published immediately so we can see what's going on in various parts of the world. Everybody contributes to the archive, the physics archive. And it doesn't matter your approach, it doesn't matter where you are, it doesn't matter your training, it doesn't matter your particular style. You can have 5 different papers come out within a short period of time, all focused on the same question, and if they are doing it correctly, they're all revealing the same answer, even if it's done in very different ways. And that's, again, one of the beauties of the language of mathematics. Natural language, you can go off in any direction. There's no constraint, ultimately. The universe provides the constraint for the language of mathematics, and that's the one piece that really keeps us tethered to reality.
And I suppose one of the challenges that you were getting to grips with in Oxford was this challenge that you mentioned of reconciling Einstein's general relativity, applying to the world of the very large, with the absolutely minute world of quantum mechanics. And how can those two worlds and those two theories be brought together? And how did you kind of engage with that, and what emerged from it?
Well, that's a huge question, which has really driven a whole body of research for a long time now. Yeah. But you're right. Einstein developed general relativity, as we mentioned, early part of the 20th century. It describes stars and galaxies using this notion of curved space-time, which is a beautiful theory. Quantum mechanics was developed in the 20s and 30s to describe a completely different realm, molecules, atoms, and subatomic particles. And it does a fantastically great job of making predictions down there. So 2 theories, each works wonderfully well in its own domain, but each, in some sense, when you try to put them together, says the other is wrong. So it's this warring hostility between the 2 pillars of 20th century physics that we in the 21st century have been trying to put together. And the first glimmers of an approach for doing that were developed by a guy named Michael Greene, no relation to me, who's now at Cambridge, and John Schwartz, in this approach called superstring theory. And it posits that our view of what nature is made of, little tiny dot particles, is the usual picture that we have in mind. Electrons and quarks, neutrinos, things of that sort. It says that if you probe them even deeper, they wouldn't be little dots, they'd be little filaments, little vibrating strings, with the different notes that the vibrating strings being able to play corresponding to different particles of nature. And amazingly, this move from a little dot, the old picture, to a little string, the new picture, winds up apparently on paper curing the hostilities between gravity and quantum mechanics, which is very exciting. But again, we don't know that it's the right theory, but at least it has a chance of being the right theory.
Could we not just live with the contradiction?
Some say that.
Live with the fact that we have general relativity and we have quantum mechanics, and just they're both true in different areas.
Some say that, and I don't understand how they can say that. Some famous people have said that. I won't mention any names, but it seems insane.
Freeman Dyson?
Freeman Dyson. You did it. I didn't say it. I don't know. I don't know how he could have said that. And maybe I just don't understand, because he's a brilliant physicist, of course. But there are domains where you need to put general relativity and quantum mechanics together. For instance, at a black hole, the center of a black hole. What is a black hole? Say a star implodes in on itself. Yeah. It's so massive that you need a theory of gravity, general relativity. But when it collapses down to an infinitesimal speck, which is what happens when a black hole forms, you also need quantum mechanics since it's so small. So here's a domain where you can't separate them out and say, use general relativity here, use quantum mechanics here. In that extreme domain, you need both theories to operate together. So you can't cordon them off. You can't sequester them in a way that would allow that dual picture to work, as far as I can see.
And how many dimensions are you currently working in?
It depends how you count and when you ask. But the version of string theory that we were developing, say when I was a graduate student in the 80s and 90s, had 9 dimensions of space and 1 of time. And that's, again, a slightly nutty-sounding idea, but the mathematics of string theory simply doesn't work if you have 3 dimensions of space, left, right, back, forth, and up, down. It demands that you have other dimensions of space. And again, just to avoid confusion, I don't sort of mean like a diagonal dimension, literally a new direction that in principle you could move in beyond the ones that we know about. How can you make sense of that? Well, you imagine that some dimensions are big, and that's why we can see them and freely navigate through them, while other dimensions might be crumpled up and very small all around us, but so tiny that we don't see them with the naked eye and even with our most advanced accelerator experiments. Now, that was the situation in the 80s and 90s. Late 90s, mid to late 90s, we learned that our mathematical techniques that we've been using to uncover these dimensions mathematically were sufficiently coarse to have missed one more dimension. And that brought the total number of spatial dimensions up to 10, with time taking us to 11 space-time dimensions. So that's the uber version of the theory that we now work with. 10 dimensions of space, 1 of time.
So 11 dimensions. And how many universes?
Again, it depends how you count. And so separate from string theory, there has been a series of developments over decades, which is exactly what this book is really about, suggesting that our universe might not be the entirety of reality. And look, that's a strange idea, right? Most of us were raised to believe that the word universe means everything, right? And I do say most of us with a degree of forethought. I don't know if my kids are here, but my daughter, who's now 5, no, she's not here, but when she was 3.5, I was holding her and I said, Sophia, I love you more than anything in the universe. And she said to me, Daddy, universe or multiverse? She had heard me talk about this stuff for far too long. But barring that kind of a weird upbringing, most of us think universe is everything. But what we have found is that from a variety of different angles, their suggestion is that reality is so much bigger than the universe that we once thought that we have coined a new term, this term multiverse. Now, string theory does contribute to this idea by suggesting its own version of multi-universes, and it comes from the extra dimensions. Because a big puzzle for decades has been, what's the exact shape? I said the extra dimensions are crumpled up, but what's the exact shape of the extra dimensions? Now, you might say, well, does it really matter? If they're crumpled up and small, we don't see them. Who really cares what the shape is? But you really do need to care about the shape, because it turns out that when these little strings are vibrating, they're so small that they don't just vibrate in the big dimensions that you and I can see, they also vibrate into these crumpled up dimensions. And just like the air that's going through a French horn has vibrational patterns dictated by the shape of the instrument, the vibrations of the string are dictated by the shape of the extra dimensions. And the vibrations are what determine things like particle masses and the strengths of forces and all the details that yield the universe as we know it. So you need to know what the shape of the extra dimensions actually is. Now, when I was a graduate student, my thesis, my dissertation, was analyzing the shape for the extra dimensions, one of the candidate shapes, and seeing the physics that comes out. And it didn't match reality. But at that point, there were only 5 candidate possible shapes. So we went back and analyzed the next one. Again, it didn't match reality. By the time we turned back to the list, it had grown. Mathematicians and physicists had found other candidate shapes, 100, 1,000, 10,000 possible different shapes. That number has now grown to 10 to the 500 different possible shapes that have been put forward as candidates for what the extra dimensions look like. The problem is, we can't possibly analyze those one by one. 10 to the 500 is more than the number of particles in the observable universe. So you can't analyze them one by one. So the suggestion has come forward that maybe what the reality is, there are many universes, each with a different shape for the extra dimensions, and we live in one universe and not another simply because our universe is the one that has that shape that gives rise to those particle properties that allow us to exist. So it's a very different vision than the one Einstein had, which was a single, unique universe that we just need to understand. The suggestion, and it is very controversial, is maybe there are many universes, each with different properties, and you live where you can exist.
And each with different laws of physics.
each with different features that would appear as though the laws of physics were different, but there is one overarching law of physics that would apply to all. But environmental differences can make those laws appear different. I mean, on the moon, gravity appears different than it does on the Earth, right? Because of an environmental difference. The Earth isn't as massive, as the moon isn't as massive as the Earth. Maybe that's the same thing with the universe is.
And do you believe, as some people have said, that everything that can possibly happen does in one of these universes?
Well, if you do take the mathematics seriously, that is the case.
Yes.
And that's sort of a funny thing, right? Because we're used to reality having features that stamp it with a certain kind of identity. And if every possibility happens, it seems like we lose our identity. I mean, that would mean that there's a universe where I'm in that chair and you're in this chair. And, you're the physicist and I'm asking you questions. It's all... I mean, when I was first talking about this stuff, I remember I gave a book talk on this in New York, and some woman in the front row, she says, well, if everything can happen consistent with the laws of physics, but variations, does that mean that there's a particle arrangement somewhere where Sarah Palin is president? And I know I'm not very political, so I didn't really know how to respond, but somebody in the back room was saying, didn't you hear the professor? The arrangement of particles must be consistent with the laws of physics. But it is a...
But there is a serious
picture.
issue here.
Yes.
Because on that basis, what system of morality can we have? How can we make decisions if effectively the world, everything that can possibly happen does? So is that a new form of determinism?
Well, it's an interesting question where free will comes into this at all, because if you're going to talk about morality, and my personal view is that free will, and many physicists feel the same way, but not all, free will is a complete illusion, right? So we tell ourselves this story that we have free will, and you need to buy into that story to live, to exist within a society. But do we really have any free will? No, I don't think so at all. When I look at the laws of physics, at least as we currently understand them, and I admit at some point maybe we'll have new laws of physics and we'll say, oh, there's free will, damn it, we missed it all these years. But now when we look at the laws of physics, there is no place for free will in those, I do think that we are just collections of particles, a bag of particles. I mean, Stephen Colbert, I don't know if you guys watch him at all here, but so I did an interview with him, and it got kind of contentious, and at the end I said to him, look, you are just a bag of particles governed by the laws of physics. And he looked at me and I was like, oh God, I hope he can pull this one out, because it's like, there's silence here. And he looked at me and he said, that's a great pickup line, But I do believe that, and I think that's all that it is.
Well, I've been predetermined to ask this question. There's Nobel laureate Philip Anderson. He is quite an outspoken critic of string theory, and he once actually described it as a futile exercise in physics. Why are people so critical? Some people very critical of string theory. What do they think is wrong with it?
Well, one overarching response I give is whenever someone's hypercritical about a subject, you should always look a little bit deeper, because there's usually some ancillary reason that's driving it. But I'm not going to analyze that at all. I just put that out there.
Not naming names.
But there is absolutely valid reasons to be very critical about string theory. And I should say that I am very critical about string theory. It has made no experimentally testable predictions that would allow us to determine whether it's right or wrong. And science ultimately is about that process. So I am hypercritical of the subject, and I don't believe that string theory is correct. What I do believe is that it's our best approach for putting together quantum mechanics and general relativity, something that has to be done. But until the theory is able to make contact with observation and experiment, nobody should believe it. That doesn't mean that nobody should work on it or should think about it or try to push the frontiers forward, or that kids can't get excited about it and want to go into physics because of the opportunities with this theory. But it does mean that you have to put it in the right context. And if we fail to do that, or if we have yet to make the balanced story out in the general public, then that's not a good thing. So when I do talk about the subject, I try to emphasize this side of it. I'm still enthusiastic about the subject, and somehow maybe that is outweighing or shading, the overall picture. But I'm as critical as they are.
And speaking of experimental physics and experimental discoveries, the last 8 days have obviously been an extraordinary time since the announcement of the observation of a boson, which may or may not be the Higgs boson, which is the amazing degree of caution with which the announcement was made. But it's a fascinating time because this week we have also the Director General of CERN in Dublin for Dublin City of Science and the ESOF conference. From your point of view, from the point of view of string theory, what does that actually mean, this discovery?
Well, it doesn't affect day-to-day string theory just yet, because frankly, we've been operating under the assumption that the Higgs particle, the Higgs boson, was the right idea and would be found. In fact, I was thinking, I don't know that I've written a single paper over the last 25 years which in one way or another did not implicitly make the assumption that the Higgs idea, that this kind of boson, this kind of so-called scalar field idea was real and would one day be confirmed. So if they hadn't found it, in a way it would have shaken up our work more vigorously than the discovery itself. But what the discovery does show is, it shows, again, like we were talking about before, that mathematics, again, appears to be the gateway toward understanding features of reality that we haven't yet been able to test. The idea was put forward in 1964 based upon mathematical calculations trying to answer a very basic question: where does mass come from? Where does the mass of electrons and quarks, the fundamental particles, where does their heft come from? So Higgs put forward this crazy idea that there's this invisible substance filling space, this invisible molasses-like substance now called the Higgs field. And when particles try to burrow through the Higgs field, the Higgs molasses, it's sticky, and that's where their mass comes from. He put forward this idea. The paper was initially rejected from the journal. Nobody believed it. But as people began to study the equations, they realized, this idea has legs. And it began to be accepted by the physics community, so much so, I have to tell you, that when I started graduate school at Oxford, 1984, people spoke about the Higgs field with such nonchalance, such confidence, that for many months I had no idea that this idea that I was learning about was speculative. I thought it was real. And then I subsequently learned, no, we don't really know that this is true. And I was like, really? And that's the state of the field. And then, as you say, a few days ago, there's finally an announcement that this idea seems to be supported by experimental observation. So it shows us that mathematical ideas can be trusted. You can't trust them all, but the techniques do take us to the truth. And that's an exciting thing for someone like me, whose work is purely mathematical.
And do you think there are still big unanswered questions in physics?
No, we pretty much have it all. No, I mean, it's huge. We've scratched, the proverbial iceberg, just the tip. I mean, even in our own lifetime, we've observed this strange thing called dark energy that nobody expected, which is driving the universe to expand at an ever-increasing rate. I mean, the expectation was that just as you throw a ball up, it goes up slower and slower because gravity pulls it back. Everybody believed that the universe is expanding, but the pull of one galaxy on every other would slow the expansion over time. The observations have shown that's not the case. It's speeding up. It's like throwing a ball upward, and it goes up faster and faster. So the big mystery is, what's pushing the universe apart? Our best explanation is that, again, there's a substance filling space invisible like the Higgs field called dark energy, which basically means we don't know what it is. Fancy word for that. And it's pushing everything outward. That's a big mystery, to really figure out what the dark energy is. Will it change over time? Will it decay? How will it affect the far future of the cosmos? And that's one of 100 questions that we could list, from where does time come from? Where does space come from? Where do the fundamental particles come from? What are the forces of nature? We know of 4. Are there others? On and on, a list of questions that will keep us busy for eons.
Fantastic. Well, I'm going to open it up soon to the audience for questions. But before I do that, I just wanted to touch on one area that we haven't really talked about, which is that you said once, and I was very taken by this statement, that science need not be experienced only in the head, but it can also be experienced fully and viscerally. What did you mean by that?
Well, what I meant by that is that, well, maybe just give an example. My mother has no idea why I do what I do, right? so I wrote, The Elegant Universe, and I gave it to her. That was my first book that I wrote back in 1999. And a few weeks later, I asked her if enjoyed it. And she said, well, she enjoyed the dedication, which was to her and my dad. I said, what about the rest? She said, well, I tried to really give me a headache, and I appreciate that idea that, for some people, science is just something up here. It stresses the mind, and it can be overwhelming and not be something that you want to engage with. But the act of doing science, when you find a discovery, when you find something that no one has ever known about before, it's thrilling. Einstein himself, when he wrote down the general theory of relativity, the first calculation he did was to apply it to the motion of the planet Mercury. There was this mystery about Mercury that its orbit was not fitting in the way Newtonian dynamics would suggest Mercury should move. So he does the calculation, and it matches the anomaly. It explains this feature of Mercury's orbit, and Einstein described that it gave him heart palpitations for hours after that discovery. That's not just in your head, that's in your body, and that's what real science is about. And I think the more people recognize that, the more people will see that science needs to be put alongside literature and music and theater and dance and art as a vital part of what it means to be human.
It's interesting. Earlier we were talking, somebody was saying that the fact that mathematics applies so well to the world is the best evidence that we're actually living inside a simulation. Would you agree with that?
One of the chapters in my book deals with that idea, because one of the ways that you could have other universes is by creating them, simulating them on a computer. And again, you may know Nick Bostrom over at Oxford. He put forward a wonderfully interesting calculation, sort of thought experiment, where if you think about it, if you try to create another universe, a real physical other universe, that's pretty hard to do, right? There actually are theories about how you might generate other universes in the laboratory, but none of them really seem to hold water. But if you were able to create universes on a computer, which would have simulated beings, like in the Matrix, that really think that they're in a universe, even though they're just bits and bytes wafting through a computer, well, if you got good at that, you could just create universe after universe by just changing this or that element in a computer program, which would mean that the number of simulated universes, if you can simulate them with such fidelity that the beings inside of them think they're real, like this one, then the number of simulated universes will far outstrip the number of real universes once you can do this. Which means that if there are many, many more simulated universes than real universes, then the odds are, just by sheer statistics, that if you are a sentient being, it's likely that you're a sentient being inside a simulation. Which is a kind of disturbing idea at some level. But then you think about it and you say, well, so what? If it's real enough, who cares if it's simulated? But nevertheless, it's a striking idea that could well be the dominant form of universe in the multiverse.
You mentioned dance and music, and I suppose one of the things that you've been very committed to is this interplay between science and the arts, and you've worked with Alan Alda, you're doing this amazing work that you've done with in collaboration with Philip Glass, Icarus at the Edge of Time, which is on Saturday, I believe, in the National Concert Hall. Can you say a little bit about that experience, what you think the arts can bring to science?
Well, I think it sort of fits into what we were just saying a moment ago. The arts, everybody knows that you take them in a very emotional, visceral way. Great music, great art, it just immediately has a direct connection to you. And science doesn't naturally have that direct connection. But if you meld science and the arts in an organic way, because I got to tell you, I've seen some versions of science and art where it brings out the worst in both. It is just awful. Okay, but if you're able to bring science and art to, and like you do here in a wondrous way, then it allows the science to penetrate, I think, much more deeply than it otherwise would. And we found, certainly at the World Science Festival, that art provides new avenues of entry into science. So there are people who wouldn't go near science, but they would go to music or dance or theater. And if that piece has a direct link to science, then you've brought them into science in a different way. So they sort of come in for the art and they leave with the science, which is wondrous when it happens. But, my experience, with Philip Glass, I think is a good one. I mean, Philip is a composer, deeply interested in ideas. And when I presented him this idea of taking this kid story about a boy going to a black hole and making it into a performance piece. He got real excited about it and really wanted to find ways to take the science and make music that was not just random, but relevant to the science. So, I mean, one night at 11 o'clock, I get a call from him, and he says, Brian, you know, I'm writing the part of the piece right now where the boy is circling the black hole and the time is slowing down in general relativistic effects. I think I've got the music for that, you know, but can you come down and listen to it, you know, see? So, you know, I went downtown to his studio, and he played the stuff, and he was so struggling and so wanting to grasp the science and find a musical rendition of it that it was great. And I think he did a great job with the score, and it really gives you a sense of how time itself has this warped quality near the edge of a black hole, which is what this particular piece is all about.
So strings doing string theory?
Well, there's actually a different piece I did with the Emerson Quartet called Strings and Strings. I won't bore you with that one, but that's actually where my first association with art came from.
Thank you. Well, if your heads haven't exploded by this point, I think this would be a good time to open it up to questions and thoughts from the audience. So, and we have two mediators with microphones who'd be happy to pass them to you. Yes, up here.
Yeah. Thank you. That was very interesting. As a scientist, at least by education, part of the wonder of science, I think, is the math content. So when we popularize science, sometimes we need to strip it from a lot of the maths. So what are we missing when we try to use analogy and explain things to people who may not have the maths depth that you do have?
You know, I think you're always going to lose something with an analogy. But I think really good analogies can at least get at the heart of the physical idea, allowing someone that doesn't have the technical training to at least get a feel for what it is that we're talking about. What you're, of course, missing is the ability to talk about it with any precision. And what sort of pains me the most, I have to say, is every so often, and I suspect you do too, I get a manuscript from somebody, and then perhaps the difference is if you've not written a popular book, I don't know if you've had, but I get a manuscript from someone who says, look, I read your book, and for the last 6 years, I've been in my basement figuring out how to go the next step. And I just want to say to them, it's just a translation of the math. There's no way you can go the next step based upon anything that's in these books, because the math isn't there, and ultimately that's the language for going the next step. And I think most people recognize that. Most people realize that you're only getting a part of the story. You know, the other side of your question, though, is you're also leaving out the beauty of the mathematics, which for many of us is the source of some of the inspiration and the wonder. And there's no way around that. And, you know, I've always had in mind to write a book about math that would try to do just that. I've not done it. It's a challenge because the language is so foreign to many people. But I think you can still get pretty far without the math in terms of getting the essential ideas.
Thank you. Do you have other questions?
Yeah, a sort of related one.
Yeah.
Is that mic on?
Yes. Yeah.
Have you had any real quantum leaps of, no pun intended, of inspiration and jumping forward in ideas in working on string theory, or has it all been just by pushing away at the equations?
Well, it's a funny thing, the quantum leap description, because as you know, the quantum leap is actually the smallest possible leap that an electron can take. Now, it is discrete, and maybe that's the part that distinguishes it. But in the popular parlance, quantum leap, of course, I think that's probably what you have in mind. And I've had a couple of moments like that, not many. I wish I had more. Work I did on trying to understand whether or not space could rip apart in string theory, something that can't happen in Einstein's theory, that so-called topology change processes. I think that came from one of those kind of quantum leaps. Another thing that we discovered called mirror symmetry, where you can have two different shapes for the extra dimensions that yield identical physical systems, different shapes but identical universes. That also came from one of those moments of inspiration that I clearly remember. But most of the time it is just pushing along, pushing the boundary along. And look, there are other people who are smarter and better. I mean, a friend of mine was a postdoc at the Institute for Advanced Study where Edward Witten, who's sort of probably the smartest person maybe that's ever lived, works. And his office shared a wall with Ed Witten's wall. And it was the summertime, so they were like the only two people left at the Institute. And my friend described to me how distressing it was to listen to Ed Witten type and type and type. 8 hours a day, cranking out paper after paper after paper. And these are sort of revolutionary papers, from brain to computer. But most of us can't do that. Most of us, it is just pushing the boundaries in an incremental way, making use of what other people have done, pushing it a little step forward.
Thank you. We had a question over here. Yeah.
I was reading a book recently by Marcus du Sautoy about finding moonshine. And he's talking, you mentioned it briefly there, about symmetries. And how life mimics symmetry, how a bee sees a flower and it's a specific symmetry, how they pollinate and stuff. And you were talking there about numbers, and it sprung into mind. And I don't know, does that have any relationship with string theories? Just in the fact that it's for like the
no, hugely so. I understand the question. Richard, I think it was Richard Feynman, said that if he was going to summarize all of science in one sentence, where we've gotten, he says that, basically matter is made up of atoms, the atomic hypothesis, sort of the most important breakthrough in modern physics. I would say the second sentence would be that symmetry underlies the laws of nature. That really has been what's driven 20th and 21st century ideas. We found that the electromagnetic force, the weak force, the nuclear force can all be bound together into a symmetric pattern, much like the points on a snowflake or the structure of a flower. And literally we can embody that symmetry in a technical manner using something called group theory. There is a certain group of symmetries in a technical mathematical sense, but you can sort of get the idea from the vernacular. The group has a name. It's SU3 cross SU2 cross U1. It just is a glorified version of the rotations that this cup respects. So this cup is symmetric under these kinds of rotation. It looks the same as I rotate it. Similarly, the forces of nature, when you rotate them in this abstract way, also look the same. And it's that structure which allowed us to work out the fundamental equations that underlie the standard model of particle physics, which is what's tested at the Large Hadron Collider. So it's all based upon symmetry. That's the key idea that has allowed us to go forward.
Yeah, thanks so much for the talk. It's really interesting to have someone who's so articulate and communicates it with such passion. I'm interested in maths education, and we were discussing in our Leonardo meeting earlier on how best can we bring maths to the public. So everybody here is obviously interested in theoretical physics and maths, but how can we extend that to just the general public without making it too technical, without going on about the beauty and the elegance to people who aren't used to it? How best can we put a poster up outside the Science Gallery where everyone will want to come in because it's maths? Do you have any ideas about that?
I have no idea. It's a tough question. It's why I've not written a popular book on mathematics like we were talking about before. I've had various ideas about how to do that. I've never felt like any of them really did the job. And I hope that one day, maybe soon, I'll have a clearer sense and maybe be able to move forward in that kind of a project. But I think it is the right question to be asking, but I don't know what the answer is.
Or is it, someone else said it at the meeting actually, should we not be focusing on it and actually just lend our attentions to the people who are interested in it? Should we not be kind of wasting energy on people that mightn't? Well, I don't believe that, but I'm just asking you.
I don't think that either. And, there have been various attempts. I mean, some attempts are obviously to show people where there's hidden mathematics in everyday things that they deeply care about. I mean, one good example, which not enough emphasis was placed on, but you remember back in the election in the United States, and I guess it was 2000, when it was, who were the people involved? So it was Al Gore and it was George Bush, right? And they were battling it out for who actually won the election. And there was all this counting that you may have followed, the hanging chads trying to figure out 500 votes here, 200 votes here. If the United States was a mathematically literate populace, people would have simply said, this is a situation where the tools for the measurement are not sufficiently precise for the attempt to do the actual measurement. If you say to someone, measure the weight of an apple to 10 to the minus 15 kilos. People know that the typical scale that we have is not adequate to the task. That's exactly the situation we were in. It's not that Bush won or Gore won. Nobody won because we simply didn't have adequate tools to measure who won. And that should have been the conversation. We should have figured out, okay, what do we do in a situation? Do you have a runoff? Don't go back and count. It's too close. There's no way to determine based upon all the errors. The errors are larger than the difference, period. And that would have been a great teaching moment for a mathematical idea that's pretty vital, but it didn't happen.
Maybe we should do a show about error. That might be one.
Yeah, absolutely.
Thank you. Other questions? Yeah.
I kind of thought that occurred to me, and it's based partly on my own experience with maths. We think of maths as this monolith, and that you like maths or you don't like maths. But in some respects, my personal experience doing computer science and other things in college was that maths is more like music. You can like jazz, not like pop. You can like hip-hop, but not like rock or something else. And that there's almost a monolithic way that we introduce kids to maths that I think colours the experience. And some people, and you can like it at certain bits at certain points. But that if we opened up the idea that there's different avenues and multiple different paths and multiple different ways into it, because I kind of found as an undergraduate, the first 2 years of maths loathed it, and the third year of maths loved it. And it was because I was doing different areas of maths, and it was different things of interest.
No, I think you're absolutely right. I mean, there's some people who love geometry because it's very visual. Someone like algebra, since it's very concrete and calculational. So, I mean, I feel the same way. There are areas of mathematics that I don't have any interest in, usually because they're just too hard for me. But there's certain kind of math that I gravitate more toward than others. And I think that's true for most people. So I think you're right.
Sorry, hello. Yeah, just a question that we meant to ask our professors when we were studying theoretical physics, and we were always too nervous to ask, which is basically, do you really think that the universe is genuinely an n-dimensional pseudo-Riemannian manifold, or whatever the current mathematical model we're using was? Or is there like a slight nagging doubt that this is just a really beautiful approximation and we're just getting more and more really beautiful approximations all the time?
So I would go even further, that I have great confidence that that is an approximation. After all, it emerges from Einstein's view of gravity, which we then have generalized. So Einstein's view that you had a 3+1 dimensional, pseudo-Riemannian manifold with various topological, Hausdorff and things of that sort. But that was a completely classical theory. It had nothing to do with quantum mechanics. And as we've tried to meld quantum mechanics into the story, various features of that picture have changed. The number of dimensions has changed, as we discussed before. But more than that, when you get to very, very small scales, there's a lot of evidence in a theory like string theory, but even in quantum mechanics more generally, that the whole idea of distance, which is what the metric does for you, that Riemannian structure, the whole idea of distance seems to be an approximate notion that only comes into play on sufficiently large scales. There is not even apparently a notion of how far apart things are if you go sufficiently small, and that's even an oxymoron. I'm talking about small as distance, but I'm saying at sufficiently small scales, conventional ideas of space and time seem to go away, which mean the conventional picture that you describe would go away too.
But the extrapolation of that therefore now is, with string theory, for example, do you, for example, believe that we live in an 11-dimensional, or is it a beautiful mathematical model which is even closer approximation?
I believe that there are certain domains of the universe where a description of reality in terms of a 10+1 dimensional pseudo-Riemannian manifold is approximately valid. There are other domains of the universe, and we can quantify that based upon the corrections that come from the quantum processes at very small scales. So we don't know that string theory is right, which is what prevents me from saying absolute certainty. But based upon an idea like string theory, we absolutely learn that there are domains where that whole story of having a geometrical space for the hypersurfaces and a time dimension that folds into it into some larger n+1 dimensional manifold just isn't right. It just doesn't work. It's not the correct description of reality on those distance scales. So absolutely an approximation is the way we look at it today.
There's a question down here at the front who's been waiting for a while, and then we're going to have to I think that is going to have to be the last one, unfortunately. I'm getting a signal. Unfortunately, I think we've run out of time. So, yeah.
Okay, yeah. Can you hear me? Yeah. Basically, you seem to be very much interested in getting to the bottom of things in the whole universe. But for me, I would say the biggest question, I never hear this talked about in science. I mean, maybe I'm just not listening enough, but basically I'm wondering, you don't seem to ask, where did life actually come from? Where did consciousness actually come from? And I would say that, like earlier he was saying, do you have any questions left? I would say that is the biggest question, and I haven't seen people asking it. So I'd like to know, is it been asked by any branch of science?
Sure. I mean, if you were to ask me what the three big questions that are on the landscape, I would say the three biggest questions are, where did the universe or multiverse come from? Where did life come from? Where did consciousness come from? Those are the big three. Now, the reason why we physicists don't talk about the life part of the consciousness part is we don't talk about it because we've got nothing to say. Those are very complicated questions. When we talk about having the standard model of particle physics that can predict the results of experiments to 10 decimal places, we're talking about applying those equations to a single particle or a handful of particles. When you talk about trillions of particles that are in some real complex interrelated relationship that somehow yields this thing called life and consciousness, that is so far beyond anything that we can speak of with any degree of certainty that we just don't have much to say. But of course, there are branches of biology and psychology, neuroscience, that do investigate, through fMRI scans, trying to get an understanding of, is consciousness merely physical processes in the brain? If it is, we should be able to line up love and joy and hate and wonder with various parts of the brain lighting up, and people are trying to map that kind of thing out. So people are trying to study the emergence of life in other environments, other planetary systems. Could they support life? So yes, people think about those questions all the time, but people like me, if we have our head on our shoulders, we don't talk about it.
Okay, and can I just as a
that was the last question.
Okay.
I'm really sorry.
The second part,
second part?
Yeah, really, it was. I meant
the first part was the origin of life, the universe, and consciousness.
Okay,
what can the second part be?
Well, can I just? My question was just that I've heard that at some levels of physics that things only happen when people are conscious of them. I mean, could you explain that?
Yeah, that's a
Yeah?
I believe that's a completely misguided idea that came from the way quantum mechanics unfolded from the 1930s. There is a real question in quantum mechanics, which is this. Quantum theory describes a reality that's a fuzzy haze of possibilities, each with different probabilities, which only becomes definite upon measurement. So the electron could be here, here, and there. You measure it, you find it here. The other possibilities go away, and there's one definite outcome. The puzzle is we don't really understand how the act of measurement caused only one definite reality to snap to the fore. We don't know what happens to the other possibilities. Do they exist in some parallel reality? We don't understand that process. It's called the quantum measurement problem. Some have suggested that since consciousness is typically involved in a measurement, maybe it's the act of consciousness that brings out a definite reality. I think that's total nonsense. What really happens is there's environmental influence that affects a system. And it's the impact of the environment, whether it's a conscious being, a computer, a photon from the cosmic microwave background radiation banging into it, and it's that interaction process that we believe is part of bringing a definite reality to the fore. It doesn't need a conscious being to be behind it. Now, you could say, how do you know that? It's always a conscious being. You always are conscious, so whenever you see a definite reality, consciousness is brought to bear, and that's one of the burdens of being a conscious being. You can't ever get outside your own head. So can we establish this? Absolutely no, because of that issue, but nothing in the laws of physics suggests there's anything special about consciousness in bringing that definite reality to the fore.
Well, that's sorted then. So I'm afraid we're going to have to end it there. And before we close, I would like to mention that we are very fortunate to have a few copies of Brian Greene's book, The Hidden Reality, which he has kindly agreed to sign if people are interested. And then I also wanted to remind you that Icarus at the Edge of Time is on Saturday. There are two performances, one at 3 o'clock and one at 7 o'clock, and I would really strongly recommend it if there are any tickets left. I don't actually know that, but if there are, I would certainly recommend you get along there. And finally, it just remains to ask you to join me in thanking Science Foundation Ireland for the support of tonight's event and Professor Brian Greene for this amazingly inspiring evening. Thank you.